So let's go ahead and take a look at some examples of generating Taylor polynomials and then using them to approximate function values. So one way to do it is we're just given information about function values and different derivative values without actually knowing the function explicitly. So here we're being asked to write a second degree Taylor polynomial for f of x with the given information below, and then use it to approximate f of 7. So when I see it says second degree, that means that when I'm done simplifying, it should have a highest exponent of 2. So what I like to do is I like to start by just writing out what it is I need to find before I start plugging anything in. So to generate a second degree Taylor polynomial, I need f of a over 0 factorial times x minus a to the 0 plus f prime of a over 1 factorial times x minus a to the first plus f double prime of a over 2 factorial times x minus 2 to the second. That takes me to the second power, not x minus 2, x minus a to the second. That takes me to the second power. I'm hoping that that's as far as I need to go and I won't need more terms. So I'm going to start plugging things in now. From here, I can see that because I'm using 3 in all of these, my center is 3. So that means this, I need f of 3. 0 factorial is 1 times x minus 3 to the 0. F prime of 3. 1 factorial is just 1 times x minus 3 to the first. F double prime of 3. 2 factorial is just 2 times x minus 3 squared. Then from the information they tell me, f of 3 is 7. But then anything to the 0 power is just 1. And then my plus sign. F prime of 3 is 16. And then x minus 3 to the first. And f double prime of 3 is a negative 1. And x minus 3 squared. And this will estimate my function for me. So there is my Taylor polynomial. Then they ask me to estimate f of 7. So that's 7 plus 16 times 7 minus 3. I'm going to change that to a minus 1/2 times 7 minus 3 squared. And I can leave it just like that because I'm not required to simplify. But if I did simplify, this simplifies to 63. And there's generating a Taylor polynomial and its estimate. Again, at a later time, we'll talk about how do I figure out how good that estimate is, in other words, what the error is, but that's not a topic for today. Second example, same idea here. I'm being asked to write a third degree Taylor polynomial and then use it to approximate f of negative 1. So if I just write out how I generate it, so a bunch of zeros, then f prime of a over 1 factorial times x minus a to the first, plus f double prime of a over 2 factorial times x minus a to the second, plus f triple prime at a over 3 factorial times x minus a to the third. I'm seeing that negative 2 is being plugged into all of these function and derivative values. So that tells me my center is negative 2. So I've got f of negative 2 over 1, then x minus negative 2 to the 0, f prime of negative 2 over 1 times x plus 2 to the first, times f double prime of negative 2 over 2 times x plus 2 squared, plus f triple prime negative 2 over 6, because that's what 3 factorial is, over x plus 2 cubed. Now plugging everything in, we get that my function is approximately f of negative 2 is 2 over 1, and then anything to the 0 power is 1. Then I have f prime of negative 2 is 10. Then f double prime of negative 2 is negative 3. And f triple prime of negative 2 is negative 3. And here is my Taylor polynomial. So then using this to estimate f of negative 1, I just need to plug negative 1 in. Negative 1 plus 2 is always going to be positive 1, so I have 2 plus 10 minus 3 halves minus 3 sixths. And again, I could leave it just like that. But if I simplify that, I get that this is approximately 10. One more example, one where we're not given a table of values. I'm being asked to write a fourth order Taylor polynomial for g of x equals cosine of 2x, centered at x equals 0, and use this to approximate cosine of 1. So again, I like to start by just going through. So g of x is going to be approximately, they tell me my center is 0, so I need g of 0 over 0 factorial times x minus 0 to the 0, plus g prime of 0 over 1 factorial times x minus 0 to the first. And I notice they're telling me order, so I'm going to need to go all the way until I get to the fourth, n is 4. So g double prime of 0 over 2 factorial times x minus 0 to the second, plus g triple prime of 0 over 3 factorial times x minus 0 to the third, plus g 1, 2, 3, 4 prime of 0 over 4 factorial times x minus 0 to the fourth. So then I need all of those values for g of 0, g prime of 0, g double prime of 0, etc. So I tend to just kind of off to the side start making my own table. So I know that g of x is the cosine of 2x. I know I'm going to need g prime, g double prime, g triple prime, and g 4 prime. And I'm doing this, and then I'm going to go through and plug in 0 for x in all of these. So derivative of cosine of 2x is negative 2 sine of 2x. Derivative of that is negative 4 cosine of 2x. Derivative of that is positive 8 sine of 2x. And the derivative of that is 16 cosine of 2x. Then from all of these, start plugging in 0 for x. Cosine of 0 is 1. Sine of 0 is 0. Cosine of 0 is 1 times negative 4. Sine of 0 is 0. Cosine of 0 is 1 times 16. And this is an example where the fourth order is going to be a bit different than fourth degree. So now going back to my Taylor polynomial and start plugging everything in, I get that g of x is going to be approximately g of 0, which is 1, over 0 factorial, which is 1, times x to the 0, which is 1, then plus g prime of 0 is 0, so actually all of that part is 0, plus negative 4 over 2 factorial, which is 2, times x squared, plus g triple prime of 0, which is 0, and everything else gets multiplied to 0 on that, plus 16 over 4 factorial is 24, times x to the fourth. The more common way is I wouldn't have written the 0 terms, and I get 1 minus 2x squared plus 2/3 x to the fourth as my Taylor polynomial. So then, using this to approximate the cosine of 1. The cosine of 1 is the same as the cosine of 2 times a half. And I have to do this 2 times a half because g of x is the cosine of 2x. So that'd be the same as the g of 1/2. So x is not going to be 1 here because my function is 2, the cosine of 2 times x. My x is 1/2. So g of 1/2 is approximately 1 minus 2 times 1/2 squared plus 2/3 times 1/2 to the 4th. And if I went ahead and converted this to a decimal or simplified the fraction, this is 13/24, or 0.5416, and the 6 is repeating. The actual cosine of 1 is approximately 0.5403. So our fourth order Taylor polynomial actually gives a pretty close estimate. I mean, we're within 0.0013 of the actual value, just using 3 terms of a quartic polynomial. So that gives you an idea of just how Taylor polynomials can be used to help us estimate functions